Okay, so we're just working on Lie algebras now, and we're mainly concerned with finite dimensional Lie algebras over the complex numbers, so that'll be my default when I use this German G. So let me see, I've given you the definition of Lie algebra, I've talked a little bit about subalgebras and ideals, and from that you get the usual isomorphism theorems which you're used to for other algebraic structures. They all go through for Lie algebras as you would expect. I think last time I very quickly gave you the definitions of nilpotent Lie algebra and of solvable Lie algebra. And finally, I gave you the definition of semi-simple Lie algebra. So that's going to be important for us. That's what we're mainly going to be interested in studying, finite dimensional semi-simple Lie algebras over the complex numbers. Remember, semi-simple meant there were no non-zero solvable ideals. I haven't given you very many examples yet, at least no examples that we've actually done anything with. So let me give you the first example. The first example is the Lie algebra SL2 of C. So this is 2 by 2 trace zero matrices. It's three-dimensional, and it's got this basis. I've written this down before, I think. E is the matrix 0, 1, 0, 0. H is the matrix 1, 0, 0, minus 1. And F is 0, 0, 1, 0. So that's kind of the standard basis, and this is standard notation, EHF, for that basis, for this most important three-dimensional Lie algebra. And you can even write down the Lie bracket totally explicitly. This is a little calculation. The bracket of E and F is H. The bracket of H and E is 2E. And the bracket of H and F is minus 2F. And that, together with the skew commutativity, and of course the Lie bracket is bilinear, that lets you work out the Lie bracket of any two elements in this three-dimensional vector space. So in fact, what I've written down there, that basis and that information about the Lie bracket completely describes this Lie algebra. And it's really worth just observing how easy it is to write that down. I've just written down a basis and a complete multiplication table. It's something that you really can't do for the corresponding algebraic group, the group SL2 of C or the group PSL2C. They're really much more complicated objects to write down. You can't hope to write down all the group elements and give a complete group multiplication table. So there's another sign that these linearized objects are really much more elementary in nature. We can just totally write this down as a vector space and give a complete multiplication table. Okay, so I'm going to prove one thing about the Lie algebra SL2, that this is a simple Lie algebra. So it has no non-zero proper ideals. And so let's give the proof. It's not really too hard. What I'm going to do is I'm going to take just some non-zero element inside G. So that's a linear combination A times E plus B times H plus C times F, a linear combination of that basis. And I'm going to let I be the ideal it generates. And the goal of the proof is just to show that in fact I is everything, and that will show that it's a simple Lie algebra. So what I'm going to do is I'm going to take this non-zero vector that's given, and I'm going to take the Lie bracket with H. So because HE is 2E, that gives me 2AE. The bracket of H with H is 0, and the bracket of H with F is negative 2F. So that means that that vector's in I. And then I'm going to take the bracket one more time with H. So I'm bracketing the vector I've just produced with H again. So I've got another bracket of H and E, which is 4AE. And then I get 4CF. That's in I. And then by summing or taking the difference in the obvious way, you deduce from that that AE and CF both belong to I. But if you've got AE and you've got CF, and of course we've got this thing as well, then BH is in I. Now, of course, some of A, B, and C could be 0, but at least one of them is non-zero. If the A is non-zero, then this gives you that the element E is in I. Then once E is in I think you can look at the bracket EF. That'll be in I, and that's H. So you get from that H is in I. And similarly here, if C is non-zero, then you get the F is in I. So when you take the bracket of that F in I with E, you get that H is in I. So this implies either way that H, in all situations, H is in I. And once H is in I, then you can just take the bracket HE, that's 2E, that's in I, and HF, that's minus 2F, that's in I. Therefore, all of E, H, and F are in I, and we've proved that I is everything. Okay, so it's totally naive, very kind of stupid proof, but it does the job. We've proved that SL2 is a simple Lie algebra. In fact, this is the smallest, by which I mean the lowest dimension, simple Lie algebra. And as we move along, you'll come to appreciate how absolutely fundamental it is for the entire theory that we are building. It's kind of the remarkable feature of this subject is that there's this very straightforward to study, this three-dimensional Lie algebra, which shockingly controls so much of the theory. It would be totally reasonable to try to classify all low-dimensional Lie algebras. Just like when you're starting out finite group theory, you try to work out the multiplication tables of all of the groups of small order, size 4, size 5, 6, and so on. You can try and classify all the Lie algebras of small dimension. So let's quickly do that, and we'll see how that goes quite quickly. So if your Lie algebra is one-dimensional, well, then of course it just has to be abelian. And there's only one, it's just up to isomorphism, it's just the field with the only possible Lie bracket, namely the bracket is 0. If it's two-dimensional, well, it could be abelian. So it's the two-dimensional vector space with 0 Lie bracket. And if it's not abelian, well, now we've got to investigate a little bit. If it's not abelian, let's pick a basis. Let's call the basis E and H for reasons that will become clear in a second. And then the bracket let's write down the bracket of H and E. So that's going to be some linear combination of the basis. It's going to be A times E plus B times H for some A and B in the field, and I'm assuming it's not abelian, so at least one of A and B is going to be non-zero. Let's assume without loss of generality that it's the A that's non-zero. Okay, and so now let's see. Let's take this vector HE, which we've just calculated AE plus BH in those terms, and let's take the bracket with H again. So that's bracketing this with H, so I get A times HE, and then B times the bracket of H with H, which is just 0. So if I replace E by HE, then I get a new, so if I just replace the E by that guy, because I'm assuming A is non-zero, that new E together with the original H, that's still another basis. And when you do this, you reduce to the situation that actually the bracket of H with this new E is just a non-zero multiple of E. And then you replace H by, let me see, I think I want 2 over A times H. And then this reduces further that actually the bracket of H with E, so if in this formula I instead plug in 2 over AH, the bracket of that with E is 2 over A times R, it's 2E. And this way we see that it's the two-dimensional subalgebra of the Lie algebra SL2 of C spanned by E and H as in the notation before. And that's it. That's the only non-abelian two-dimensional Lie algebra. It's kind of the upper triangular matrices in the Lie algebra SL2. This is a two-dimensional solvable Lie algebra. The derived subalgebra is just that is spanned by E, but the center of this Lie algebra is trivial. It's not nilpotent. Okay, so that's two-dimensional, and then I guess you should then start thinking about three-dimensional. That would be very reasonable to do. So what can we do? Well, we can take the abelian one, or we can take a direct sum of C and the two-dimensional one just studied. That gives some non-abelian three-dimensional Lie algebra, and so those aren't new ones, they're just kind of built by taking direct sums of the old ones, and then there's going to be lots more three-dimensional ones which we haven't seen anything like before. In fact, there's a bunch of three-dimensional Lie algebras that you can construct by using the notion of semi-direct product. So you've seen semi-direct products for groups, and there's a similar analogous notion for Lie algebras, and a good way of constructing three-dimensional Lie algebras is to take the abelian two-dimensional Lie algebra and form a semi-direct product with a one-dimensional Lie algebra. So I'm not going to kind of go into detail for this. You can take any Lie algebra G and any other Lie algebra N, and you can build this new Lie algebra called semi-direct product. And to do that, what you need is a Lie algebra homomorphism from the Lie algebra G to the Lie algebra of derivations of N. And that is the data that, with that data, then it's quite easy to cook up a non-trivial Lie bracket on the direct sum of the vector spaces G and N that isn't the direct sum of those Lie algebras. It's kind of a twist of that using this homomorphism from G to der N. So I'm going to leave pondering all of that to you. So we're taking a semi-direct product with the two-dimensional abelian Lie algebra being an ideal. And it's easy to see that derivations of that, well, that's the whole Lie algebra GL2. So any 2x2 matrix determines that Lie algebra homomorphism. So that's the input that you need, a 2x2 matrix to construct such a semi-direct product. And then you realize that actually it's 2x2 matrices up to similarity. So you get a bunch of families of semi-direct products from conjugacy classes of 2x2 matrices. And so in particular, you get continuous families of of three-dimensional Lie algebras from different kind of Jordan normal forms for your 2x2 matrices. So that's interesting. I'm not going to kind of go through all the different types, but you see how that goes to classifying this type of three-dimensional Lie algebra that's a semi-direct product. And one thing you see from that right away is that there's uncountably many three-dimensional Lie algebras up to isomorphism, and most of those are not going to arise as the Lie algebra of a three-dimensional connected algebraic group. Whereas in dimensions 1 and 2, all of the Lie algebras are indeed Lie algebras of groups. As soon as you hit dimension 3, there's many Lie algebras in these families which don't arise as Lie algebras of groups. So that's a sort of typical phenomenon. Somehow groups are much more precious than Lie algebras. Okay, so that's the whole load, but still that doesn't give. And by the way, these first two examples, they are such. They are just kind of degenerate examples of such semi-direct products. So actually, I've only really given you one family of examples at this point coming from semi-direct products. And then there's another interesting three-dimensional Lie algebra called the Heisenberg Lie algebra, which has basis x, y, z, and the Lie bracket is defined so that the bracket of x and y is z, and then z is central. So the bracket of z with everything is 0. So that completely tells you everything you need to know to write down the Lie bracket of any two vectors in the three-dimensional Heisenberg Lie algebra. This actually you can think of this. It's a semi-direct product as well, but it's a semi-direct product of the one-dimensional Lie algebra being the ideal. That's the ideal spanned by this central element z, and then there's an abelian two-dimensional Lie algebra on top of that. So this, by the way, is most of these semi-direct products are solvable but not nilpotent. But this Heisenberg is actually nilpotent because it has this non-trivial center, and then when you factor that out, when you factor out the center, you've got an abelian Lie algebra. So these are almost all solvable. With except for the abelian example, right? Almost all are solvable, but not nilpotent. And then there's just one more, which is the Lie algebra SL2 of C that we've already talked about, which is actually simple. So I think that's just, I haven't gone into massive detail about that classification. It's I think it was actually first worked out by Bianchi. I was looking up a little bit of the history. So this was first done in 1898. Actually, Bianchi did this over R, not C, where it's actually a little bit more interesting because there's more similarity classes of matrices to think about. And actually, when you go over R, there's, for example, there's two three-dimensional simple Lie algebras over R. There's SL2 of R, but there's also another one called SO3 of R, which it should be very familiar to you. That's just the vector space R3, where the Lie bracket is the usual cross product of vectors. Over the real numbers, these two are non-isomorphic, but when you extend scalars, from R to C, these become isomorphic. So over the complex numbers, there's only one three-dimensional simple Lie algebra, and that's our SL2 of C. And we're always working over an algebraically closed field, But this is a kind of just one glimpse of the interesting things that will happen when you go down to non-algebraically closed fields, the real numbers being the most important one to do. And always actually the right way to think is to think about how to descend from the complex numbers to more general fields. So this story over the algebraically closed field C is the beginning of the classification for other fields. Okay, so anyway, so we're getting a few examples. That's a good sign. So I want to talk next I want to talk a little bit more about representations. Of Lie algebras. So this is going to be our main tool in studying Lie algebras, is by thinking about representations of them. So let's actually now finally give you the definition. We'll say that a vector space V is a G module. Somehow I've got to this point without introducing this language before. A G module if there's a bilinear map from G cross V to V such that, so I'm going to just denote this as sending an X in the Lie algebra and a vector V in the vector space V just to XV, just as you would normally write for a left module. There's one axiom that I want this bilinear map to have, which is if I take a vector and I act with a y and then I act with an x, or I act the other way, I first act with x and then I act with y, that's got to be the same as acting with the Lie bracket xy on V. So that's it. That's the only axiom that I need for a module. If V is a G module, you get a Lie algebra homomorphism rho from the Lie algebra G to the general linear Lie algebra GL of V, sending x to rho of x, where rho of x is the endomorphism of the vector space V, whose value on a vector is just xv. And conversely. So in this way you see that the notion of G module is just exactly the same data as the notion of representation, Lie algebra homomorphism, rho from G to GLV. And as usual, you use the two languages interchangeably. You talk about modules or representations, and whichever's more convenient in what you're doing. There's also an obvious notion of a homomorphism of G modules. So that's a linear map which intertwines the actions. So this is for all vectors in V and X in G. If you were thinking in terms of representations, you would have a diagram like this commuting. So this if V and W are two G modules, a morphism F, it's a linear map, which makes this diagram commute. So this would be rho V of X, the representation of X on V, and rho W of X. This is for all X in the Lie algebra. So it's just the same notion in there, written in the language of Lie algebra homomorphisms. Okay, so we're going to be very interested in representations of our Lie algebras in G modules in this sense. So now we come to the most important definition today. So this is any Lie algebra. I'm defining what's called U of G. So this is what's called its universal enveloping algebra. So let's actually give this a fancy box, because this is now a really important notion. So it's denoted just U of G, the universal enveloping algebra of G. This is the associative algebra. It's an associative unital algebra. So here's the definition. So you take the vector space G and you form the tensor algebra. So that's the free associative algebra on that vector space. And then you quotient out by the two-sided ideal of that free associative algebra. You quotient out by the two-sided ideal generated by all x tensor y minus y tensor x minus xy for all x and y in the vector space G that generates the tensor algebra, the degree 1 part of that graded algebra. Okay, so that's the universal enveloping algebra. There's then a linear map. I don't know, maybe I'll just write I from G to U of G. I guess I'll just write X maps to X bar often. This is just the canonical map, right? The vector space G embeds into the tensor algebra, and then the tensor algebra surjects onto the universal enveloping algebra because it's a quotient of the tensor algebra by definition. I guess at this point it's not obvious that this linear map is itself injective. We will see that, I guess, next time, that it is injective, but nothing that I'm saying today depends on knowing that, because it's not something that's immediately clear from this definition. Because this ideal that we factored out, look, these are degree 2 tensors, whereas this is in degree 1 in this tensor algebra. Okay, so let me see. This linear map is actually, it's even a little bit better. It's actually a Lie algebra homomorphism. If we view the associative algebra U of G as a Lie algebra via the commutator. Remember, any associative algebra can be viewed as a Lie algebra by defining the Lie bracket to be the commutator. So this I is not merely a linear map, it's actually a Lie algebra homomorphism, and that's automatic because of the relations that we've imposed in constructing this U of G. It's automatic that the commutator of x and y in G map under this map I to the same thing as the image of to x bar bracketed with y bar in U of G. So in fact, U of G is the associative algebra which is universal for this property. Let me write down the property properly. So we've got this Lie algebra G, we've got the universal enveloping algebra U of G, and we've got this linear map I. If you have A, any associative algebra, and you have F, any linear map, which is a Lie algebra homomorphism for the induced Lie bracket on A, right? So A is an associative algebra. You can think of it as a Lie algebra by defining its Lie bracket to be the commutator. And I want this F here to be any Lie algebra homomorphism from G to that associative algebra A. Well, then the universal property is that there exists a unique F bar, an algebra homomorphism, a unital algebra homomorphism, making that diagonal commute. And the proof is it's really just one of those automatic nonsense proofs with universal properties. Because remember, the universal enveloping algebra was constructed from the tensor algebra by taking the quotient by that two-sided ideal. The tensor algebra is the it's the free associative algebra on the vector space G. So it's automatic that this F extends uniquely to an associative algebra homomorphism from T of G to A. I haven't used the fact that F is a Lie algebra homomorphism yet, merely a linear map. So that's the universal property of the free associative algebra on the vector space G. But then because actually F is a Lie algebra homomorphism, this induced map F1 sends all the generators of that ideal to 0. And so then we can then use the universal property of this U of G defined as a quotient to see that this F1 factors through the quotient to give you the F bar that we want. Okay, so I'm not going to write any words because I think that's one of those routine universal property arguments. So what we've just done is we've mapped G to an associative algebra. It's universal enveloping algebra. And we've got this canonical map I, which is a Lie algebra homomorphism. And then somehow that's the universal associative algebra that we can map our Lie algebra to. So why is this important? Well, here's a lemma. If V is a G module, there's a unique way to make it into a module over the associative algebra U of G, so that x bar V equals xV for all elements of the Lie algebra. And conversely, any left module over that associative algebra becomes a module over the Lie algebra in the earlier sense by defining the way x acts on V to be x bar V for all x in G. So this is just an application of the universal property that I just defined. You see, because the tensor algebra is generated in degree 1, the universal enveloping algebra is generated by all these x bars. So if you want all the x bar v's to be these x v's, there's no choice. So that's the uniqueness for how this U of G action comes about. U of G is generated by the image of G under this map I. And to check that that's a well-defined action, you just have to use the definition of U of G. So it's, of course, you have a module over the tensor algebra, and by the definition of G module, it's automatic that all of these generators of this ideal act as zero, and so that the action, so the way the action extends to the tensor algebra factors to make it into a module over the universal enveloping algebra, and vice versa. So in fact here, this is an isomorphism of categories. From the category of G modules, so representations, and the category of U of G modules, left modules over this associative algebra. Maybe I should add the word left in there. So this is great because there's this well-established theory of modules over associative algebras, and now we see that having a module over a Lie algebra, it is just the same as having a module over this universal enveloping algebra. And so in fact we have the whole theory of representations of Lie algebras just as a special case of the general theory of modules over rings. Let's just run through a few examples. I guess we should start out with the abelian Lie algebra. So if you pick a basis vector, let's call it x, then the universal enveloping algebra of that. So what's the tensor algebra of the one-dimensional vector space on basis x? Well, that's just the polynomial algebra, and because the Lie bracket is 0, we're basically not imposing any relations, and so by the very definition, the universal enveloping algebra in this case is just the polynomial algebra in one variable. So in this case, because we're pretty good at modules over this PID, we understand G modules completely in this case. For example, the one-dimensional ones, well, they just correspond to the points lambda in the field, so we have x acting as the scalar lambda. The finite dimensional G modules, well, remember your theory of finite dimensional modules over this PID C of x, so these correspond to the Jordan normal forms. The Jordan block, if you have a Jordan block like something like that, Jordan block, these give the indecomposables. Okay, so that's great. That's one case where we totally understand at least finite dimensional G modules. But even this case is kind of interesting, right? Because this G, it's the Lie algebra of the one-dimensional torus, the multiplicative group, and this we understood that all GM modules, all representations of that multiplicative group. I didn't use that language, so I should use representations. All representations of the multiplicative group were completely reducible, and in particular the irreducible ones were one-dimensional, and they were labeled actually by integers. Remember, we had this functor from representations of the algebraic group to representations of its Lie algebra, and so we're seeing in this case this connection between the Lie algebra and the group. It's not super tight. The group has not very many, a kind of rather discrete collection of irreducible representations, whereas the Lie algebra has a continuous family indexed by complex numbers. So only some of these representations come from the representations of the group by passing to the differential, only the ones indexed by integers. Not only that, all representations of the group decompose as direct sums of these one-dimensional ones, whereas we're seeing for the Lie algebra that Jordan blocks give us a whole load of indecomposable representations. So this is just a silly example, really, but you're seeing how this correspondence between the group and the Lie algebra it's not very tight in this case. And maybe that's not so surprising, because you can also think of this Lie algebra as being the Lie algebra of the additive group. There you don't have complete reducibility, but in that case the only irreducibles actually actually you only get the irreducible where lambda is 0 for that group, but you do get Jordan blocks coming up. So anyway, this Lie theory correspondence going back and forth between groups and Lie algebras, you can always go from the group to the Lie algebra in this functorial way, but the connection is not necessarily as tight as you would like. It's only really when you have semi-simple Lie algebras that the connection to semi-simple groups is perfect. That's the main situation for this Lie theory principle. Okay, so that's one example. Second example, let's take the Heisenberg Lie algebra. So remember that had these generators x, y, and z. You can write down very easily what the universal enveloping algebra of Heisenberg is, I'm just going to write it. It looks like the polynomial algebra in the variable z, and then you have to adjoin x and y, so it's the free associative algebra in non-commuting indeterminates x and y over this polynomial algebra in z. Okay, so z commutes with everything. Remember, z was central in the Heisenberg Lie algebra. So Heisenberg, the bracket of x and y was z, and z was central. And then on that you have to factor out a two-sided ideal, because you have to force that the commutator x, y is equal to z. So that's the universal enveloping algebra of Heisenberg, and maybe that looks familiar to you. Maybe it will look even more familiar if you set this central element z to 1, and then you get the free associative algebra in x and y, and this idea becomes xy minus yx minus 1. This is the first Weyl algebra, which is the kind of first example of a non-commutative associative algebra that you often think about, which is this non-commutative deformation of the usual commutative polynomial algebra in x and y. Okay, so I wanted to say just one last thing today. Let me see if I can do that. So we've talked quite a lot about Hopf algebras. And if G is a finite group, well, its group algebra CG it's a Hopf algebra. So remember, it's already an associative algebra. You need a co-multiplication and a co-unit. I usually use delta and epsilon for the co-unit. And in this case, the co-multiplication is the algebra homomorphism, which on a group element is G tensor G, and the co-unit on a group element, it sends it to the element 1 in the ground field. We also talked about if G is an algebraic group, we talked about the coordinate algebra. And again, that's a Hopf algebra. In that case, the co-multiplication was the co-multiplication was indeed the comorphism of the multiplication on the algebraic group, and the co-unit, well, that was evaluation at the identity element. So the coordinate algebra of an algebraic group, maybe I should write down the antipode as well here. Let me do that. So I usually use capital S for the antipode. So for the group algebra of a finite group, the antipode is defined on group elements. The antipode on G is G inverse. And for an algebraic group, the antipode, that was the comorphism of the inversion map. So to complete this, if G is a Lie algebra, then the universal enveloping algebra is a Hopf algebra, and the co-multiplication on, so I'm going to take x in G here. So then I had this x bar, remember that was the image of x under the canonical map from the Lie algebra G to its universal enveloping algebra. The co-multiplication on x bar, it's given by x bar tensor 1 plus 1 tensor x bar. The co-unit on an x bar is 0, and the antipode of x bar is minus x bar. So these uniquely determine algebra homomorphisms. Actually, S is an algebra anti-homomorphism, but delta and epsilon are algebra homomorphisms defined by these formulas. And to prove that these exist, you have to use the universal property of universal enveloping algebra to prove that there is such a unique such associative algebra homomorphism delta and a unique such associative algebra homomorphism epsilon from U of G to the field, and a unique such associative algebra anti-homomorphism S. I remember for the coordinate algebra S was actually an algebra homomorphism, but just because this was commutative. Even in the group case, this is an anti-homomorphism, this antipode. So I'm not going to go through very much of that, but let me maybe just write down to construct delta. You have to check that if you take the bracket of an x bar tensor 1 and a y bar tensor 1 in U of G tensor U of G, that is the same thing as the bracket of x and y, tensor 1, plus 1 tensor the bracket of x and y in the Lie algebra. So you check that, and then that gives you a Lie algebra homomorphism from G to U of G tensor U of G, sending x to x bar tensor 1 plus 1 tensor x bar, and then you use the universal property. Okay, so so these are three examples of Hopf algebra: group algebras of finite groups, coordinate algebras of algebraic groups, and universal enveloping algebras of Lie algebras. We will. So in each of these three cases, we've got a notion of representation. A representation of a finite group, is the same as a module over the group algebra. We've just been discussing how a representation of a Lie algebra is the same as a module over its universal enveloping algebra. And on homeworks, you've seen how a representation of an algebraic group, it's not a module, it's actually a co-module over the coordinate algebra. So this is just three analogous situations. And so I'm going to talk a little bit more about this at the beginning next time. But the reason it's important that these algebras or co-algebras are actually Hopf algebras is it lets you define a tensor product, a tensor structure on these categories of modules or co-modules in all three cases. So I'll explain how that goes first thing next time.